All right, how's it going, everybody? We are here at the beginning of week 7. We're going to introduce the normal distribution today. We're going to look at our first couple sections in chapter 6 here. This is going to be super important for us for the rest of the semester. We're going to be pretty dependent on the normal distribution to help us compute all probabilities of interest. Why it's more important than pretty much every other distribution will be what we're going to discuss in tomorrow's video. So today we're going to look at how to sort of use the normal distribution to help us understand some probabilities of interest, and given some probabilities, determine some values of interest, kind of going backwards as well. And again, in tomorrow's video, we'll look and see why is it that the normal distribution crops up in so many places. There is a big idea called the central limit theorem, and it's going to tell us that a lot of taking samples of things, even if the underlying variable itself is not normally distributed, we'll still see the average values of results be normally distributed. And that's going to be a really big idea for us here this year. So today and tomorrow, we're talking all normal distribution. And again, this is very much not a 1 week topic. This is sort of setting ourselves up with the one of the most essential computations we'll be doing for the rest of the semester here. It is the case today that at the end, we'll be looking at how to use technology to do a bunch of the computations we need to do. So I've got written out what you can do for the TI calculator computations, and then I will also demonstrate the Excel computations. And the good news is that these should follow very similarly from what we've been doing with the binomial distribution. TI calculator people will see a little bit of a difference. The Excel computations, though, are very consistent with what we were doing with the binomial computations here. The other thing that's going to be better is that we're going to have a much easier way to draw diagrams of what we're thinking about when we're talking about the normal distribution. So I think that'll actually make our computations, in fact, a little bit easier than they were with the binomial distribution, since we didn't talk too much about the graph of the binomial distribution. However, the normal distribution is it's got the bell-shaped curve that I think we've all seen before in some context or another. And consequently, it's going to be easier for us to draw diagrams to help us kind of reason our way through what we're thinking. So let's go ahead and get started. And the way that I want to start this one too is to help remind ourselves of where we've been with the distributions that we've looked at so far. So let's kind of just briefly walk through some of the features that we've seen of distributions we've already discussed so that we can see the normal distribution in context of what we've already seen. So the first thing that we did, importantly, was we talked about our binomial distribution. The binomial distribution is discussing the probabilities when, and by the way, here's our important things that were on the test. There are 3 conditions required for us to consider an experiment to be a binomial experiment. Is the bi in binomial says there needs to only be 2 possible outcomes. We need it to be the case that the probability of success does not change depending on the previous outcomes that we've seen. That means that we need each trial to be independent of one another. We can't have a change in our probability of success. And finally, we need to have a fixed number of trials that we are performing, not some unknown number of trials. Those are the 3 things we need for a binomial style experiment here. The outcomes of a binomial experiment will be distributed binomially according to the binomial distribution. This is a discrete probability distribution because all of the outputs that our random variable are going to take on it's always only one of 2 choices, right? So we don't have a spectrum of choices. As in a continuous distribution here, it is discrete because there is a fixed number, limited number of only 2 possible outcomes. If we determine that a variable is binomially distributed, our mathematical notation for that is to say the variable itself is x. This might be, male or female, or it might be the 2 outcomes that x could take on. The tilde symbol is our as is distributed as right there. Binom, the name of the distribution, usually a shorthand right there, binomial distribution. And what we've seen is that the 2 parameters that we have to understand what they are to define a binomial distribution are the sample size, n, and the probability of success, p. But this is unique to the binomial distribution. Other things don't require a number of trials or a probability of success. For example, when we're talking normal distribution, when I'm talking about average adult male height, there isn't some probability of success. There's not a success that's defined in that context, right? So this NP being the defining characteristics of the binomial distribution is unique to the binomial distribution. We did see very briefly that I wrote out this formula here. This is what we call the probability distribution function. This is a computation that you could do to compute the probability of seeing exactly k successes here. The reason why we never did this one by hand is because this n choose k is I don't know, that would have taken us another little day of math discussion to get into computing some of these things here. And I felt like because we're going to head off into technology computation for the normal distribution anyway, I think it was perfectly fine that we just went to technology to do these computations rather than trying to do, our n choose k times p to the k times q to the n minus k right there. This is really just saying multiply together all of your the number of successes that we want to see. If we're going to see k successes, if we're seeing k successes, then out of the n total trials, k were successes, so n minus k would have been failures. So this is saying we also want to see n minus k failures if there are k successes. But what we know is that those could be arranged in many different ways. The example that we wrote out was something like wondering if it was something like 2 out of 5 flights were going to be on time, but we saw there was 10 different ways that we could choose the 2 on-time flights out of the 5 overall flights. That's what we were getting from that n choose k, and that can get to be quite a large number right there if you have lots of trials, lots of number, and a moderate number of successes. So the point here was we did get a formula, but we never ever directly used the formula except for like one time when I was demonstrating it in the example there, and it can get to be a little bit hairy out there. So we just let technology do this for us. The final thing I want to say about the binomial distribution, because this is a discrete probability distribution, there is probability associated with getting a single event. If I were to say to you, if I go poll 100 people, what is the probability that I see exactly 14 males out of 100? There is a probability that that will happen, right? On the other hand, if we're saying things like, what is the probability that I am exactly 6 feet tall? We're going to go ahead and say it that has 0 probability because exactly 6 feet tall means like literally exactly 6 feet tall, like 6.00000000 feet tall, right? You might say, what is the probability that I am within a quarter inch of 6 feet tall? And I can tell you what probability that might be. We can compute that one. But a distinction that we want to make here is that when we talked about our continuous probability distributions, we said that the probability of an event is equal to the area underneath the probability distribution function's curve. And if we're looking at the probability and again, I'm talking about our opposite scenario here, not what we're looking at here, in a continuous probability distribution, if we were looking at something like the probability that x equals 6 or the probability that my height is exactly 70 inches, well, that's just going to be one stick, and a stick doesn't have any area, right? It's like a rectangle with no width. And so in discrete probability distributions, there is probability associated with individual events, whereas continuous probability distributions, there is not. The next one that we looked at was the uniform distribution. Interestingly, the uniform distribution is one of the, I don't want to say like rare, but it's pretty uncommon that we can use distributions either as discrete or continuous. We generally think of the uniform distribution as being continuous, but then again, our kind of first example of something that was uniformly distributed was rolls of a die. And when you're rolling a die, there are exactly 6 possible outcomes. That is a discrete distribution right there. So the uniform distribution really can kind of belong to both camps there a little bit. What we needed to know to define the the uniform distribution was just the lower and upper bounds. What's the lowest possible and highest possible value we could possibly take on? And we knew that we could take on anything in between that with all equal probability. When we notate this, again, we're saying our random variable is x. The tilde says is distributed according to. The name of the distribution is the uniform distribution. And in the case of the uniform distribution, we don't, where we're using different parameters to define the distribution. In the binomial setting, we needed a number of trials and a probability of success. In the uniform distribution, we define the distribution by the upper and lower bounds of the possible outputs that we might see. We also have a formula to compute this, but honestly, I don't think I ever even wrote this formula down, and that's because I don't think I have to, based on this paragraph that's down here. So let me draw a picture that kind of discusses the last couple things that I've said here. When we are talking about our uniform distribution, everything is equally likely, and therefore the probabilities are all the same. If our probability on our graph is height, then that means that our heights should be the same. So a typical uniform distribution is always going to have this rectangular shape here. Lower bound is A, upper bound is B. What must my height be then here? Well, I know the total area is 1, and that should be our length times our width. It looks like our width here, the width of this rectangle, is we get all the length of B, except we don't have any width associated with A, right? So B minus A would be our width here. And so we can see that this height right here should be 1 over B minus A. That should be our height right there. And if we wanted to find any probability that our variable x would take on some value less than k, for example, then we could go ahead and do that computation here by determining where k is going to be, right? If k is some value in between a and b, then this right here should be the probability that our value takes on a value of less than k, right? This should be our probability that x is less than k right there, that amount of area. And so what you can see here is that this is a rectangle here. This should be a length times width. My length, I guess I'm thinking of length as like my height right here, because I'm thinking of width as horizontal. My length or my height right here is the 1 over b minus a, and my width here is k minus a. And so you can see that that exactly matches what I've written right there for that probability statement. But the point is, when you guys did this, like, these were pretty easy. It's just the area of a rectangle. So I don't think it was even necessarily directly meaningful to state a generic equation for this right here, because I think in most cases it's easier for you to literally just draw the rectangle than it is to try and reference a formula and come up with what your 3 different parameters are and kind of sub them in and stuff like that. So the point here was computing probabilities with the continuous or with the uniform distribution was pretty easy, because the probability of any event is equal to the area under the curve associated with those events of interest. And therefore, all we had to do was find the area of a rectangle to compute probability. That was really easy here. So the nice thing that I like is that the mix of what we did with the binomial and the uniform is this. In the binomial distribution, we sort of learned, hey, sometimes we're going to want to just let technology compute values for us. In the uniform distribution, what we learned is in any continuous distribution, the area underneath the probability curve is equal to the probability of that event occurring. And these two concepts together are going to be exactly what we're going to need to be able to handle our normal distribution stuff. So again, maybe my last thought right here, because this is a continuous probability distribution, typically we think of this as continuous here. Although, as I said, we do have discrete settings for uniform as well, like rolling a die. The probability of seeing one specific outcome is 0. So if I'm thinking to myself in the above picture that literally any number between A and B is possible, then you should understand that there are an infinite number of numbers between any two numbers. That's sort of the density of the real number line right there. So if there's an infinite number of numbers between A and B, then your question of what is the probability that I pull this one particular number out of an infinite number of numbers should be 0. Again, you should think to yourself, what if we were just looking for the probability that x is equal to k in my diagram there? Then my rectangle would have 0 width. It would just be really like a vertical stick, and there is no area under a point. We have to have area under an interval to actually accumulate area here. So where are we at then for today? Today we want to talk about the normal distribution. So we've already seen how I laid out the previous two distributions. I'm going to give you basically the same information here. The normal distribution is a continuous probability distribution. Very importantly, the normal distribution is symmetric. Because it's symmetric, the mean, median, and mode are all the same as each other, or all will be essentially the same as each other. We know that when we collect samples, we always will see a little bit of variability, so they might not be identical. Because it's symmetric, that means that we can make the choice to use the mean and standard deviation. In general, we prefer the mean. Whenever we use the mean, we always will stick with the standard deviation as the measure of spread. And so our normal distribution here will be defined based on the mean and standard deviation. Notice that we are using these Greek letters to define these things. You're going to see these a million more times this semester, so you should learn how to say these. This is a U with a stick on it right here, and this is pronounced like mu. And this is a sigma right here. It looks sort of like a little whistle. That's a sigma. Mu and sigma. This is, I mean, these are, I guess this is technically spelled mu right there, pronounced like mu. So if a random variable x is normally distributed, I'm going to try and be responsible here and capitalize n so that we can know that when I say normal, I don't mean like regular, but sort of like the formal stats definition of normal, as in following the bell-shaped curve. Then we notate it as, and again, you're seeing the same structure of notation here. The random variable x, so like adult male heights, are distributed. The normal distribution is here's a great indicator that everybody cares more about the normal distribution than anything else. Its shorthand isn't norm, it's literally just capital N, because everybody that knows in any probability or statistics computation that if you see that capital N, we're probably referring to some normal distribution thing. I feel like to think that the number of the lesser the number of letters in your shorthand, the more it's a commonplace thing that everybody recognizes. And again, here we're always going to have mu and sigma as our defining parameters here. And importantly, will always be in this order. So it's going to be the case plenty of times for the rest of the semester that I'm going to give you information where I'm just going to say, hey, we've got this random variable x here. And what I expect is that you are easily able to interpret this as saying, x is a random variable. It is distributed according to the normal distribution. It has an average value of 10. It has a standard deviation of 1.3. And I just know that because 10 is sitting in the same slot as mu. 1.3 is sitting in the same slot as sigma right here. So it'll always be mu then sigma. I will never, ever switch that order on you. It's always going to be average then standard deviation. As we saw with the binomial distribution, sometimes these equations make us uncomfortable. You should look at this equation for 1 second, go ahead and lean over and throw up in the trash can, and then realize that you don't ever want to touch this equation right here because it's absolutely terrible and difficult to deal with. This equation is unfortunate. Let's just say that right here. It would be really, really nice if we got things like just rectangles like we got in the uniform distribution so we could do easy computations by hand. That's just not the case here. What I do want to point out to you, I guess, is this beginning chunk out here, this is gross, 1 over sigma times the square root of 2 pi. Unfortunate, but you know what? It's really just some constant out there. Really, when I see equations or like this, I want to say to myself, like, but what's the x doing? Like, mu and sigma can vary. There's an infinite number of normal distributions for all the different combinations of mu's and sigmas that could ever exist out there. This is really, in a sense, more like our true variable x right here. And so I do want to just say, this is sort of like e, which, by the way, if you haven't taken algebra, you might not even know what we're talking about with e. Yeah, unfortunate to say the least, but we're going to round about it. E to the power of negative, and then, you know, some constants of 1/2, a constant of mu, a constant of sigma, e to the negative x squared. And so even if we kind of wash away all the crap here, that's still a very difficult function to deal with right there. E to the negative x squared. There are many properties associated with probability distribution functions that we have a strong desire to do calculus with, by the way. So I'm going to say 60 seconds of calculus things here. What we have learned is that the area underneath the curve is equal to the probability of that event occurring. And so when we look at a normal curve, we might say, oh, I'm interested in computing this area right here. This will tell me the probability that, that my son will be shorter than 5'5" or something like that. A little bit shorter than average is what I'm seeing right there. Well, what we would want to do then, if we were a calculus student, is in calculus you will learn that to compute the area under a curve is to compute an integral of a function. So we would want to compute the integral, perhaps from the lower bound of going all the way to the left, negative infinity, up to the upper bound of like our 5 foot 5 inches or whatever that's going to be right there. The very unfortunate thing is that this is literally not possible. There's no amount of calculus that you can learn that makes that actually a doable computation. That's unfortunate because that means that we can't ever get like true exact computations associated with this single variable normal distribution, which is really, it's like, well, damn, it's like the one thing we want, and it can be proven that it can't be found exactly. I think it's worth pointing out, literally what I am teaching in my Calculus 2 class this week is exactly how do we come up with approximations for area underneath funky curves like this when it's otherwise impossible. Literally this week in Calc 2, I'm teaching exactly what do we do because we're stuck right there in the calculus sense, right? So the integral of e to the negative x squared, literally not doable in calculus, and this week, exactly, I am teaching approximation techniques to come up with that because of the fact that it's not technically exactly findable, which is heavily disappointing because Uh, Otherwise, we're going to struggle to get these direct values right here. Now, our calculators, Excel, everything else is going to do a great job of giving us approximations that are going to be accurate to 8, 10 decimal places, whatever we want, way more accuracy than we ever really need. So it's okay that we can't get like a true exact number for these because we can achieve any level of accuracy that we desire with these approximations. We don't have to do any of the work. Our calculator in Excel will do all the work, but it's an interesting like little pickle out there. It's like a highly desirable function that we would like to integrate in calculus is not integrable, and that's disappointing. So in any event, this is the equation of the probability distribution function. This is the thing that gives you a graph that is a bell-shaped curve. But quite unfortunately, it's difficult for us to manage in this class. You really need a bunch of calculus to understand what's going on with it. And even once you get to calculus, the first thing you're going to talk about is the fact that even with the calculus, we can't truly get the answer either. And so this normal distribution is something that is ubiquitous, right? It's everywhere. It kind of governs lots and lots and lots of probabilities. It's messy and sloppy. And so technology is going to be our friend because technology is going to mean you don't have to deal with any of the messiness that's associated with this. So take one last moment, stare at this a little bit more and say, ugh, one last time, and then we don't need to worry about that equation literally ever again. As I say right here, uh, even if you're going to be like a statistician, you're really not going to screw around with this equation until you get to grad school, when you're really just going to do more things of talking about how hard it is to manage. So that's just to say that equation is never at any point your responsibility here. It's worth seeing to see that it's gross. Now that we've seen how it's gross and difficult to manage, we won't deal with the equation directly. Your calculator, Excel, understand how to make good approximations of this equation, and they will, and that's what we need to trust. Again, because this is a continuous probability distribution, there is no probability associated with a single event. In my little tiny picture that I've drawn up here, you can see that there is area under a curve that we could measure. But if I said, what is the probability that I am exactly 6'2", then that's just the area under a point. And there is no area under 1 point because it has no width right there. So we are always going to be looking at probabilities of intervals. There's always going to be less thans, greater thans. If it's ever an equal to probability for a continuous distribution, it'll always just be 0. There's no area under 1 point on a curve. So let's go ahead and take a look a little bit more closely about what we're going to end up seeing with the graphs of the normal distributions here. Importantly, I have tried to emphasize, but I don't think I emphasized enough here, that what we really would like to do with any distribution is describe its shape, center, and spread. What shape does the distribution take on? How do we describe the center of the distribution? And how do we describe the spread of the distribution? In a normal distribution, the shape is always a bell-shaped curve. We're actually also going to see a second distribution this semester that is also mostly bell-shaped. It's technically not the same as this. It's going to be very close, though. And we'll also see some distributions this semester still to come that are not the shape of anything that we've seen so far. Since this is a symmetric distribution, very important that we understand that this is symmetric. The left side is always going to perfectly match the right side, at least theoretically here. Again, when we take samples, there's always a little bit of variability, but a normal distribution is a symmetric distribution. Since it is symmetric, we can always measure the center to be the average. So what I'm going to do is I'm going to mark this tick mark right here. And by the way, I'm going to add some like vertical lines to kind of help me see some visual things here. But that's mu. That's my average right there. We are centered at the average. Normal distributions, we will measure the spread of normal distributions because they're symmetric. We get to use our preference of average being the center. Every time we use average as our measure of center, we will always use standard deviation as the measure of spread. So I am, and again, I know that a very small minority of us have calculus experience that are in this class, but this is some interesting things that I can't talk about these things without bringing it up. One of the things of interest here is that you should notice that this point on this curve, there's something special at this location right here, which is that if we wanted to measure the slope of this curve at any place, you should see that this curve is pointing upwards right here, right? We have positive slope over here, positive, positive, positive slope. Over here, the curve is pointing downwards. We have negative slopes over here. But right at this average right here is the one place where the slope is equal to 0. It turns out that in Calculus 1, one of the first major things that you learn in calculus is how to measure the slope of a curve. In algebra, we measure the slope of straight lines, but it's kind of weird to think about the slope of a curve instead because it's always changing. One of the important things to identify here is that the average, the x value that is the average right here, the x value, I'll live my axes, the x value at the average is the one place on the curve where we're going to see a slope of 0. So this is a calculus-defined average right here. Where our standard deviations are is also going to be a calculus-defined term. And again, I know that most all of us don't know about these things, but for the few that do, this is really worthwhile. For the few of us also that will then go on and take some calculus, it's cool to know, kind of to be able to think about some of these things here. So I'm going to draw these little kind of like guidelines just to help me visualize this right here. Each of these tick marks is intended to represent one standard deviation of distance right here. So this guy right here is our x location, that is one standard deviation above normal. This tick mark here is one standard deviation below normal. And when I say normal, I mean average right here. Right? So if we're one standard deviation above average, I could indicate this as mu plus sigma, right? It's our average plus one standard deviation. This is one standard deviation above normal. Here is 2 standard deviations above normal. Here is 3 standard deviations above normal. Right? And we could do the same thing going back the other way here. Mu minus sigma is right there. 2 standard deviations below average and 3 standard deviations below average. I really should be saying average here. That normal, when I say normal, I mean the middle. And in this case, that's going to be the average. I said I have a calculus statement that I want to make here. And here's the calculus statement I want to make. Here, this is where we would say our calculus statement about this straight line right here is we would say the derivative, the slope of the curve, is 0 when x is at mu because we have a horizontal line. What you can visually see right here, let me just make that an x right here, where this location is. How do you know about how far one standard deviation is away on a bell curve? And here's how we can see this. What you can picture, I don't think it's super obvious just by me marking those X's on there, but here's what you should be able to see with this. Another thing that we'll go to compute in calculus is the concavity of a curve. And this is asking the question, does the curve bend downwards or does the curve bend upwards? And what you can see where those two X's are right there, right at one standard deviation above and below normal, is that's right where our graph switches from being concave down, bent downwards at the middle part, to being concave up, bent upwards on the outside parts. And you can certainly see it. There's a bend upwards on the outside, but certainly a bend downwards on the inside. And right where it switches from bending down to bending up is exactly where we'll experience that, that one standard deviation. So for those couple calculus folks out there, where the second derivative of that gross function up here is equal to 0. If you take 2 derivatives of this thing, which would be miserable, and then set it equal to 0 and solve, you would find that x equals mu plus sigma would be exactly what you're going to get. That's exactly, you'd get 2 solutions. X equals mu plus or minus sigma. It's the 2 locations where we switch from being concave down to being concave up. So if you're, and by the way, I know that I'm saying a bunch of calculus things right now, but I'm just saying to you, if you just generically flop a bell-shaped curve on paper and you're like, where should I estimate one standard deviation away to be? Just look at your curve and see where it's transitioning from being bent down to bent up. And exactly at that point right there, that's where our one standard deviation away should be. I'm not going to get too crazy with these and yell at you about being slightly wrong with these. We all need to be drawing diagrams in this unit, but I'm okay with our diagram. I've seen some funky looking bell-shaped curves in my day, I can assure you. So as long as our diagrams serve our purposes, then we're good to go here. So this is kind of our generic idea of what all of our bell-shaped curves are going to look like. They're always going to be centered at the average, which we notate with mu, and we're always going to want to identify a few standard deviations away in each direction. And let me make a quick statement right here. Another thing that I can see is this, and I want to kind of point out a few things real quick here. It looks to me like this curve is almost down to 0 by the time we get to 3 standard deviations away. Now, what I know is it's not like nothing is ever more than 3 standard deviations away from average. My good example that I like to go to all the time is like Shaq. Shaq is like 6.1 standard deviations taller than average or something ridiculous like that, right? Yao Ming, he's like the 14th tallest person in the world or something like that, NBA players, and he's like 7 standard deviations above average in height. There, I think actually there's, we'll do this computation I think next week. I think there's expected to be only like 2 people on Earth that are of the same height as Yao Ming based on the fact that he's like 7 standard deviations above normal. So the point is, this graph technically keeps on going forever to the left and to the right, but holy cow is it so close to the x-axis that we are barely accumulating any area, any probability associated with those events. So what we can take away from this diagram right here is this. This graph does go forever to the left or right. So I want to say this. So this graph does go forever. I might say from negative infinity to positive infinity, but it looks like almost all members of the population are within 3 standard deviations. And this is a good, very generic approximation for us to make right here. So on the one hand, we want to really understand that, yeah, it's technically possible to observe results that are 100 standard deviations above average. But those things are like literally like, you know, we're talking 1 in the trillion to the trillionth power probability of seeing things that are that unlikely, right? Crazy unlikely events, but they could happen. This distribution does go forever, left and right. I wish that you could see my arms as I stretch out all the way out here. But what we're really seeing is that since we know that in any continuous probability, the probability of an event occurring is equal to the area underneath the curve associated with that span of events, that you should see here that almost 100% of the area that's going to be underneath that curve is accumulated between 3 standard deviations below and 3 standard deviations above. We can't even draw the gap between the curve and the x-axis. It's so close for pretty much forever on out there. So we are technically accumulating probability, but it's crazy small, right? So a good general thing for you to think of is essentially all things will fall within 3 standard deviations of the mean. And it's not really all, but like 99.9%. I think it really is. I think 3 standard deviations, like 99.98% of all observations will be within 3 standard deviations of the mean. And so it's pretty reasonable for us to like think of this in our heads as pretty much everything's within 3 standard deviations of the mean. We consider things that fall within 2 standard deviations of the mean to be typical. And we're going to come up with a general approximation for that here in a moment, right? So, we're going to draw lots of diagrams that look like this. You should notice that when we measure 3 standard deviations above and below average, that there are 7 x values that are sitting here on the x-axis. You're going to draw quite a few diagrams the rest of the semester that are going to have 7 appropriate values on the x-axis, just given the specific mu and sigma for your event. Then we'll draw that diagram. So let's look at an example of that here. So let's draw some comparative graphs. By the way, I forgot we're going to do this real quick right here to make sure that we kind of see how these things compare to each other. So what I'm giving you here is changing our parameters that are defining this normal distribution. So on one single set of axes, I'm going to go ahead and draw 2 different bell curves so that we can compare the 2 of them. So first, I want to compare the x variable and the y variable here. The x random variable here is normally distributed with an average at 20 and 5 as the standard deviation. So here's the thing that I'm thinking. This is going to be my mu for x right there. It's my average value for the x distribution is 20. What I learned in the above graph is that if I go about 3 standard deviations away, that's essentially getting all the information that I need to get, at least for my loose diagrams, right? I'm not trying to draw something crazy technical here. I'm just trying to draw a diagram that really gives me the impression that I need to have of this distribution. So I can see here that my standard deviation, I'm going to call that mu x and sigma x right there. My standard deviation of x is 5. So I'm going to go 1, 2, 3 standard deviations away over to here. And I kind of feel like that's going to be sort of like where I'm going to basically stop drawing my bell-shaped curve, because I'm not going to draw a million miles of bell-shaped curve on the x-axis left and right. Similarly here, I should be able to go 1, 2, 3 above right here. And so I'm thinking that I should be drawing some bell-shaped curve that is centered at 20 and that spreads essentially from 5 to 35. It does go forever. I'm pretty much always just going to draw about 3 standard deviations worth of stuff. So here's my first bad bell-shaped curve. Oh man, these are so hard to draw. Oh man, that was horrendous right there. Bad job, Tony. But here's the really important thing about this, where I'm trying to draw some comparative graphs right here. All right, so this is our x distribution right there. If we want to compare this to this guy over here, what we should notice is that here our average is now 40. So our distribution will be centered at the x location of 40, or the y location of 40. And notice it has the exact same standard deviation here. This is the important part. So since our spread of values are the same, I am again going to walk 1, 2, 3 standard deviations to the left. I think that essentially all of the y values that I'll ever see are going to be as small as 25. And very rarely we'd see one smaller than that, but like so rarely I'm not going to graph it. And similarly, 1, 2, 3 above would say 3 standard deviations above normal for the y parameter, for the y variable here would be 55. So this would be saying to me, if out of all the population of y stuff right here, almost all of our results will be between 25 and 55. That is within 3 standard deviations of average, 3 below and 3 above. And so what I should draw here, and here's what I'm going to try to do to help myself. The point to me is this. Since these two guys are spread the same, we should be seeing, oh my gosh, that's just the worst curve I've ever drawn in my life. Okay, I need to note this. Horrible drawing. Curves should be identical, just horizontally shifted. So the point I'm trying to get across here is, because the standard deviations are exactly the same, the area, the spread of the area of our two curves should be exactly the same. The only thing that changed here was the average went from 20 to 40, and all that did was move the location of our normal distribution, because the center is what got moved. How spread out the data were exactly the same, a standard deviation of 5 in each case. And so we saw them go 15 below and 15 above for just as far as we draw. And again, I'm going to keep saying it. These curves really do go forever and ever out there, but they just get infinitely close to the x-axis. We're barely accumulating any area at that point. And since area is probability, and probability is what is of interest, this is essentially the meat of what's going on right here. All right, so we've drawn our y curve and our x curve, and I think this is the simpler of the two cases, where the standard deviations are the same, but where the averages are different. So again, these two curves are intended to be identical to each other. One just shifted 20 units to get to the other out there. So let's play this game, but see the more interesting version of it here. Now you should notice in our second example here, again, we're going to draw 2 on the same curve, but here's the difference. This guy has an average of 40, and so does y. X and y are both going to be centered at 40 for their average. The difference is that one is quite spread out with a standard deviation of 6, and the other is much less spread out with a standard deviation of 2. So what this means to me is that this data should be far more spread out. The y data should be far more spread out than the x data. And here is the big key. Read the sentence that's at the bottom of the screen right now. Remember that the area under any probability distribution is 1. So if we increase how spread out the data are, then it's going to result in the bell-shaped curve being lower and flatter, because the area is fixed at 1. We are always going to have a grand total amount of 1 square unit as the area underneath any bell-shaped curve. So the more spread out it gets, just imagine that you're literally like pulling it wider. It should be then therefore getting, in a sense, shorter over that process. On the other hand, if you have a very small standard deviation, then that means that your results aren't deviating much from the mean, and you should get a very high probability of seeing stuff close to the mean, and then immediately a small probability of stuff being further away. So this spread is actually going to change really the shape of our graph pretty meaningfully here, all right? So both of these guys are sitting here at 40 for the average, right? So both of our graphs are going to be centered at 40. The difference, though, is that the x values here, this has a standard deviation of 2. Since it's a small standard deviation, I'm expecting a pretty tall bell curve out here. And what I know from my earlier statements, where it looks like about 3 standard deviations mostly covers what we are interested in here, at least for our diagram drawing, that says to me I'm going to go 1, 2, 3 standard deviations to the left. And by the way, you should notice that I have already smartly numbered my axes to set myself up for the day. It's going to matter that you are able to like compute a couple numbers above and below. 40, we're dropping by 2s 3 times. So 38 is 1 standard deviation below. 36 is 2 standard deviations below. 34 is 3 standard deviations below for x. That's not true for y, right? And similarly, we'll go 6 units above, because 6 units at 2 units per standard deviation is 3 standard deviations. So what I'm expecting to see here is this x guy should be tall and skinny because it doesn't have a very big spread in its data. 2 is a relatively small standard deviation, at least compared to 6. And so I'm expecting to see my bell-shaped curve exist pretty much just between. Okay, that's a little bit better right there. Better than my last ones were anyway. So there is my x curve that I'm looking at right there. Now, again, the area underneath every single probability distribution function curve is always just 1. The area never changes. So if our standard deviation gets much, much larger out here, it's pulling it wider, which is going to squash it flatter out here. So notice now, if we're interested in representing our 3 standard deviations above and below in our y variable, we're still centered at 40. But now 3 standard deviations above is going to be 18 above 40. That's going to get us out to 58 for our 3 standard deviations above. So this is our mu sub y plus 3 sigma y. Right? That's our average plus 3 standard deviations for y. Similarly, we're going to go 3 times 6 is 18. We're going to go 18 units below 40 to get to our, our diagram's lower bound out here anyway. And that will put us, what, at 22, right? That's 14 minus 80. So this is going to be our mu sub y minus 3 sigma y is our 22 right here. So now I'm going to draw the worst bell-shaped curve I've drawn all day right here. But the point to me is this. Since our data are so much more spread out, I'm expecting a very low peak, right? Because our area has to be stuck at 1 right here. So I don't know. That's just my estimate right there. But I'm going to try and draw. Okay, not very bell-shaped, but still, that's maybe my y parameter right there. So the point is, it's very spread out because we have a much larger standard deviation. But these were both centered right at 40 right there. They both had the same average of 40. So I'm doing some comparative diagramming with these is really important because it helps us get a feel for our probabilities. Some of the things that I can see now are things like this. Let me just make 2 comparative statements. When we are pulling random samples from the X population here, this guy, what I can see is that there's a pretty good probability that we'll experience events between 38 and 40. Look at all the area that we're getting right here between 38 and 40. But events between 36 and 38 are much less likely to happen. There's much less area between 36 and 38 on the X curve than there is between 38 and 40 on the X curve. Big difference. On the other hand, if we go look at our y distribution and think of those same intervals, under the y distribution, the low flat curve out here, the area underneath 38 to 40 is almost the same as the area underneath 36 to 38. I can certainly see that the area under 36 to 38 is less than 38 to 40, but not by much, right? So here we're seeing because things are so much more spread out, it sort of helps us make some sort of like intuitive guesses about like what kind of probabilities are we going to see. We could say things like, it looks like for the X distribution, we're 2 or 3 times as likely to see something between 38 and 40 likely as we were between 36 and 38. But for the y distribution, we're barely more likely to see something between 38 and 40 as we are between 36 and 38. And that's because there's a much greater spread, a larger standard deviation of the area. So let me kind of just wrap up this picture by saying I got a bunch of very good and reasonable questions from people about interpreting standard deviation associated with the binomial distribution in the last couple of weeks. And I basically kept on saying to those people like, it's a little harder to talk about. We're not really focusing on the graphs of the binomial distribution. We'll be able to see it better in the normal distribution. Now is when you should be able to kind of see the influence of the standard deviation and what it's doing for us right here. It's spreading out our probabilities, or if we have tiny standard deviations, it's packing up all of our probabilities very close to the average, saying you're not going to deviate from the average hardly at all if you have a small standard deviation, and therefore almost all results should be very, very, very close to the average right there. All right? So some comparative graphing with these, I think, is a good thing to visualize for yourself right there. So now that we've seen some examples of these and we've kind of hammered home this idea that while 3 standard deviations above and below doesn't cover everything, it covers pretty dang close to everything, to the point where I never really draw anything beyond 3 standard deviations in my diagrams ever. We certainly will see, you can definitely bet that we're going to end up seeing some things where we're going to discuss things being 15 standard deviations above and below normal this semester. But I'm never going to draw a graph where I draw all the way out to 15 standard deviations. We want to kind of develop this graphical intuition here, and that pretty typically always happens by saying, draw a graph that shows, where we're at within 3 standard deviations above and below. So let's take a look at an actual example here. Rather than just using mu and sigma everywhere and just using our notation everywhere, let's look at an actual example. So IQ is, keep on missing capitalization. IQ is normally distributed with an average of 100 points and a standard deviation of 15 points. By the way, just so that you know how this actually works, it's not like people made up a test and just magically people's average was 100. The test scores are designed specifically to be with an average of 100 and a standard deviation of 15, just to help make interpreting the values a little bit easier here. So this is a test that was the numbers of your scoring on the test. I mean, they could have made it work out to be anything. They just set it up to be some nice numbers right here. So first things first, how do we notate this using our normal distribution notation? Here I would say that IQ is distributed normally with an average of 100 and a standard deviation of 15. So that sentence in the example is equivalent to that notation that I just wrote down. There's no information I missed, and there's no other information in the sentence. IQ is normally distributed with an average of 100 and a standard deviation of 15 points. Graphically, then, we can draw where this distribution looks like here, right? So I'm going to say 100 is my average, and I'm going to draw several standard deviations above and below. If you are 1 standard deviation above normal in IQ, then you have an additional 15 IQ points above average. So that'll be 115. Another 15 will get us to 130, and 145 will get us 3 standard deviations above. Similarly, I can subtract 15 at a time when I'm going to the left. 1 standard deviation below normal would be 85. Another would be 70. Subtracting another 50, 75, I said 70 at least, is 70. And another would be 55 out there. So what this is saying to me is mostly all people, and again, we're going to talk about this probably later, but it turns out it's 99.98% of people are going to have an IQ between 55 and 145. That's generally true about humans. IQ, as with many, many biological things, is normally distributed here. And so this is my first route to kind of imagining the probabilities that are associated with this. And we'll come back to this picture in a minute and throw some percentages on here. For now, what I want to do is look at a couple computations that are associated with the standard deviation here. Suppose a person has an IQ of 94. How many standard deviations away from average are they? Well, let's first measure just how far is their IQ from average. And the way that I'm going to compute this is I'm going to do mu minus my x value of interest. So here, by the way, we're saying that our observation x is 94 in this case, the observed value. We met a person, their IQ is 94. That's the one observation. That's our x value there. To compute mu minus x is to say what is the difference between the average value and the one that we observed. So here that would be 100 minus 94. And I'm going, oh wait, I want to, sorry. I'm going to set this up a little bit backwards. Or I set this up backwards. I still want to say that x is 94. But I want to phrase this slightly differently, and you'll see why in 1 second right here. We're still saying that our observed value is 94. This is still subtraction between our observed value and the average, so it's still going to measure the difference here. But what you'll see here is that putting them in this appropriate order right here will indicate to us the right sign. This is saying to me this person is 6 IQ points below average right there. That's what the negative is telling me, is it's a below average score right there. So what I didn't want to know was just how many IQ points away, but how many standard deviations away. So now we can say, I don't want an I right there. What am I writing? So how many standard deviations away is -6. And so I can just divide -6 by my number of standard deviations. Or by the size of a standard deviation, I should say. We just figured out that x minus mu is -6. We saw above that our standard deviation size is 15. And so this person's not many standard deviations below normal. I'm going to go to my calculator now, 6 divided by 15, and I'm getting 0.4. And I'm going to call this a letter Z here. You guys just hang on to yourselves with that one. We'll come to this in 1 second here. What we have determined is that if you have an IQ of 94, then that means that you are 0.4 standard deviations below normal, because you are 6 IQ points below normal, and with a 15 IQ points being 1 standard deviation, we are clearly only about like a third of a standard deviation, right? 5 out of 15 would be 1/3 of 1 standard deviation. We're a little bit more than that. So we've got 0.4 standard deviations below normal. And so notice here, 94 has units, 94 IQ points, right? That had units on it. Oh, what was that? Oh, come on, computer. "94 IQ points." Here, we've divided 6 IQ points by 15 IQ points, and we've ended up with a unitless answer of, in a sense, our answer has the units of number of standard deviations away. But again, we've kind of lost the in context unit right here. So in any event, our computation here has shown us that of x minus mu over sigma has given us the count of standard deviations away from average that our observation x is. So x is in context, it is the true observed number. Z is sort of removing the context. It's just a measure of standard deviations. It's unitless unless you're considering the units to be the number of standard deviations. And as long as we get our sign correct, as our ordering correct on top of x minus mu instead of mu minus x, then the positive or negative will exactly tell us were we above or below average right there. So let's go ahead and flip this question around now. Now we're going to say, suppose a person has an IQ that is 1.5 standard deviations above normal. What is their IQ? And by the way, what I should have been doing over here, what a responsible professor would have done if I was thinking right here, is I'd be drawing these things in a diagram, right? If I'm thinking 94, then where I can see that 94 is at is like right there, right? There's my 94 location. Maybe I'll switch my colors right here. This is my 94 location right there. I was just barely below average right there. We can see certainly not even a half of a standard deviation. I can measure that visually. Similarly here, our next question is 1.5 standard deviations above normal. Well, 1.5 standard deviations above normal has to be like right there. So we can see that we can, in a sense, like visually estimate this right here. We don't want to try and get too cocky about our visual estimations here. We do want to do some computation instead. But I do want to maybe just mark this as saying like this is our 1.5 standard deviations above normal, above average, above mu right there, above average. right? So I can see that I'm expecting a number that I guess is going to be exactly halfway between 115 and 130. So let's see what we can do to make this computation happen right here. So what I'm thinking to myself is I really want to get into IQ, right? I've been given a number that's not in terms of IQ. So I'm going to say 1.5 standard deviations. And I'm going to write this out a little bit long form for myself. I don't typically write it like this. I'm just going to do this once right here. What I'm going to do is I'm going to do a little bit of unit math right here. I know that one standard deviation is the same thing as 15 IQ points. And I can see here, I'm going to cancel standard deviations as units. Oops. Oh, yeah, I have that right here. So it looks like this should be 1.5 times 15. And that's going to give me, if I go to my calculator, 22.5 IQ points above average. All I want to know then is what's average, and I can add that up then. So then I can say from this guy right here, I can say 100 plus 100 plus the 22.5 is going to give me an IQ of 122.5. Right. Let's look back at our graph, and then we'll generalize the equation that we just used right there. We were looking for something that was halfway in between 115 and 130. We came up with 122.5, and you should notice 122.5 is exactly 7.5 above one standard deviation and 7.5 below two standard deviations. So it's exactly halfway between 1 and 2 standard deviations above, and that's perfect because we were 1.5 standard deviations above right there. So it looks like what we just did, it looks like our computation here was we multiplied together our number of standard deviations sigma times our observed value. And then what we really did is we added that to our average here, right? So, and that was getting us our, sorry, I said oh, hang on. I said that wrong. I'm gonna go back here. I said a bad thing right there. What this 1.5 is, this is our number of standard deviations. Our number of standard deviations, as we did in the previous problem right here, we denote with z. Z is our number of standard deviations. Let me just write this. Z equals number of standard deviations. So it looks like what we did here is we multiplied z times sigma. We really realized that that was just going to give us how far we were from average, so we needed to add that to the average. So it really looks like what we used for our formula is mu plus z times sigma equals, and what this gave us then was our answer in the context of the problem, right? Just like an IQ of 94 was x up here, an IQ of 122.5 is x down here. So it looks like these should basically be our two sort of equivalent equations right here. And what I have in the boxes up here and the box down here are exactly equivalent to each other. This is just our equation solved for z equals x stuff. This is x equals z stuff right here. So if you know your number of standard deviations and you want that in the context of the problem, then you can use this red box right here. If you know your value in the context of the problem and you want to know number of standard deviations, the opposite situation, then you can use the stuff in the box right here. And honestly, I really only ever think of this top one right here because I know that I can just do the algebra to solve for x if I'm ever interested in doing so. And so maybe let me kind of just do that right here. Let's just kind of see that these are the same. Z equals x minus mu over sigma. I can multiply both sides by sigma. And then I can add mu to both sides. So these are equivalent to each other. These are the same thing. One is just solved for x and one is just solved for z. So this is how we can get our in context x information into out of context number of standard deviation information. And that's going to be really practical for us here. We're going to be very interested in computing number of standard deviations to help with a lot of our technology computations here. So I'm kind of just formalizing what we just said right here. Typically, we use z to denote the number of standard deviations. No context of the problem, no units. It's just number of standard deviations. And we use x to denote the value of interest in the context of the problem with units. So x is truly what we observed. I am 68 inches. That person wears a size 10 shoe versus saying Shaq is 6.3 standard deviations above average in height. It's just a count of standard deviations. That's Z information. So what we just came up with to sort of summarize what we saw is in the first example, we were given an X value of 94 IQ points, and we determined that was the equivalent of 4 standard or zero point 0.4 standard deviations below average. In the second example, we were given the number of standard deviations, in this case above average, and we determined that to be a in-context interpretation of 122.5 IQ points. Right? Again, units go with X stuff, units with X stuff. Z is just a count of standard deviation. So this is just the results that we just got from the previous page there. So distinguishing between X and Z is important here. Remember that X is in the context of the problem. X should always have units. Z is just a count of standard deviations away from average, and it shouldn't have units unless you're just identifying the units as number of standard deviations. In general, we call all these Z things Z-scores, just the name of these things. Z-score is just a phrasing for number of standard deviations, is all it is. So we're going to really care about Z-scores this for like the rest of the semester here. It's going to matter that we can compute Z-scores. We just dealt with Z-scores right there. We just didn't say that until just now, so that's good. So dealing with Z-scores isn't that bad. If you need to manage Z-scores, then these are the two equations that you've got to be able to handle to do that. Either take a z-score and get into context, or start in context and get to a z-score. These are just the forwards and backwards versions of each other. The reason that we really like z-scores is because they help us compare non-comparable items out there. Because as we've seen, things are distributed differently. Not all distributions are the same. There's an infinite number of different normal distributions out there, all for different mu's and sigmas. But we still might want to say, like, well, what's more likely? That we'd see our x value be 46, or that we'd see our y value be 51, or something like that. We can try and make those computations if we can get our things out of the context of their variable and into a generic context of z-score. So z-score sort of strips away the context and allows us to make generic comparisons across things that otherwise wouldn't be comparable. So let's do an example of this. And in fact, you should have seen an example sort of like this previously this semester here. So hopefully this looks vaguely familiar to you. Here where I'm saying we've got two non-comparable things, women's shoe size and adult male height measured in inches. It turns out that in the United States, adult women's shoe size, the average shoe size worn by women is about a 7.9 with a standard deviation of about 1.8 sizes. Similarly, adult male height in the United States, and adult male height, by the way, is distributed differently in like every country. We're like the second or third tallest country on average, but I think like Norway and Finland or something like that have taller people or something. Maybe it's Sweden, I'm not sure. I think it's a Scandinavian country that has the tallest people on average. So adult male height in the U.S. is approximately average with or approximately normal with an average of 68 inches with a standard deviation of 2.5 inches. And so what I want to know is which one's more unlikely, a woman wearing size 10 shoes or an adult male being 5'5". And obviously the point here is that these aren't directly comparable because we're not measuring the same thing. Because I can't compare shoe size to height in inches, I need to get to a common ground of a z-score where I can compare them. Since I know that they're both normally distributed, I can just say, well, whichever one's further from average is the more unlikely one. Let me just say that right here. right? What I know, what I can see in my normal distribution graph is that the further you get from the average, the lower the graph gets, indicating that there's less and less and less probability of seeing those further and further away events in standard deviation. And so I'm thinking if I can find out which one is more standard deviations away from its average, then that's the less likely outcome right there. So which is more likely, a woman wearing a size 10 shoe or an adult male being 5'5"? And again, I'm not even going to compute the probabilities of these events. I'm just going to compute how many standard deviations away each of these are from average and make a direct comparison from there. So our first one, women's shoes. What I've been given here is I've been given according to my distribution that mu is 7.9. I've been given sigma is 1.8, and I've been given that my observation of interest here is a woman wearing a size 10 shoe. That's my observation of interest. In the case of the adult male height, which I'm going to abbreviate AMH, I use adult male height as my example so often, just get used to that one right there. We've been given that our average is 68 inches, our standard deviation is 2.5 inches, and our observed value of interest is being 5'5", which, by the way, 5'5" doesn't help me because I need to be just in straight up inches right there, right? So 5 feet is 60 inches, plus another 5 inches gives me 65 inches right there. So what we can do is we can use this information now to compute how many standard deviations away from average each of these observations are. So we used the formula above a moment ago. I'm doing it the exact same way backwards as I was before. Z equals x minus mu over sigma. And in this case here, we're going to get shoe size of 10 minus 7.9 divided by 1.8. So what I can see that we're getting here is that we are 2.1 standard deviate, or sorry, we are 2.1 shoe sizes above average with a standard deviation of 1.8. We'll go to our calculator in a second. Similarly over here, I'm going to set up my exact same computation, x minus mu over sigma. In this case, that will be our observed value is 65 minus our average value, which was 68. And that is out of a standard deviation of 2.5 inches. I can see in this case that this person is 3 inches below average, but that's out of 2.5 as a standard deviation there. So now we go to our calculator and see which one of these has a more extreme z-score. 2.1 divided by 1.8 is giving me 1.167. And 3 divided by 2.5 is giving me 1.2. So it's very close right here. We can also see an interesting observation to make here is that our adult male height was below average. That's what the negative is telling me. Our women's shoe size was above average. That's what the positive is telling me. But I also know that because this is a symmetric distribution, I know that I'm just looking for distance from the average, right? So our adult male height was 1.2 standard deviations below normal. Our women's shoe size was 1.167 above normal. So it looks like in this case here, we can see that the adult male height is more unlikely. Let me just write it right here. Looks like 65 inches of adult male height is slightly less common than a women's shoe size of 10. It's further from average. All right, so we computed some z-scores. They were super close. Tough to eyeball that one right there. It doesn't help me to know that this woman was wearing 2.1, a size that was 2.1 sizes above average, and that this person was 3 inches below average. I needed the standard deviation in there to standardize how we're measuring this stuff right there to get into that z-score. And so in this example, we couldn't directly compare the x values. So we converted into a common z-land to where we could make a direct comparison between these two. So what's really happening when we use this formula right here? I want to kind of show you a nice little graphical thing that happens right here, a little quick series of graphs. If I'm graphing my x values, where x is distributed normal mu sigma, then what I know is that we are looking at just some old distribution that's out there somewhere out in space, right? And it's going to be out there something like this, right? And we've got, our mu plus sigma, we've got our mu minus sigma out there, right? It's just somewhere out, and we're centered out wherever mu is, right? So what's happening as we perform this computation? Well, the first thing that happens in this computation is we subtract off mu from all of our x values. So imagine that we've taken a sample of 50 people's heights. Well, let's subtract off the average from all those heights. Then what that should just leave us with is just how many inches above or below normal are you, right? So since I am like 1 inch above average, x minus mu for me should be 1, because I am 1 inch above average, right? I think actually I'm 2 inches above average, whatever. The point is that now we've moved this graph, we have shifted this graph to where we have subtracted mu. So if we subtract mu from all these x values, we've really just moved it over. Notice where mu was, mu minus mu is 0. We should be centered at 0 now, and we should still be at 1 sigma above and 1 sigma below right there, and on and on. Now is our next step. Now we take all of these x minus mu values that are now centered at 0, and now we're going to divide everything by sigma. So you should notice if this tick mark right here was at a distance of sigma away from the x-axis, sigma divided by sigma is going to be 1. So now we're landing at a graph that is centered at 0. And because we've divided by exactly our standard deviation, we are now experiencing just a standard deviation of 1. So these tick marks are now representing our standard deviations from the mean of 0. But this is now what we will come to call our standard normal distribution. This is, we have standardized all of our x things by subtracting their average and dividing by their standard deviation. This is now our common ground from which we could make broad comparisons to other distributions that are different than the one that we might be observing, just like we did in this example up here a second ago. All right? So when we perform this computation of converting from x into z, you should kind of picture us not just changing one value into a different value, but we're really taking a whole distribution. We're shifting it to be centered at 0, and then we're shaping up the spread so that the spread is exactly 1 standard deviation per unit. And that's exactly what we've got with our last graph right there. So in general, we say that if any x variable is distributed normally mu sigma, then if we convert to z using our formula here, then now we should land in a normal 0, 1 distribution. And man, this is one of those things where it's like, if you got to pick any number, like I'm going to say to you, like, you get to choose the functions that you use and the numbers that you use to do math with. Like, clearly none of us would ever come and be like, yeah, I think I want to do math with this function right here. Nobody would ever choose that. Similarly, if you got to pick the numbers to do math with, you should pick the nicest numbers that there are, and 0 and 1 are about the nicest numbers that you could ever choose to do math with. So getting into the standard normal distribution is getting us into a place where it's as easy as possible for us to think about the math in context. When we do things like, say, even these distributions right here, these aren't too bad, but still, like 7.9 and 1.8, like a little bit of a bummer. It's hard for me to like visualize, right? I couldn't do this problem in my head because those numbers were slightly not nice enough that I had to do some written work and go to a calculator. 0, 1 as a parameter for our distribution makes things a lot nicer to work with right there. So this is our standard normal distribution. Let me just circle that and say this is our standard normal distribution right here. It's where we have an average of 0, we're centered at 0, and 1 unit is 1 standard deviation. It's our standardized distribution. So let's look now at computing some probabilities for some things. I do think I'm getting a little, maybe getting a little bit long here today. We might bump our technology things into tomorrow. That's okay. I think that's what I'm going to do. I'm going to do the empirical rule today, which is how do we approximate probabilities associated with the normal distribution. And just because we're already at 1 hour and 15 minutes, I don't want to go longer than 1 hour and 30. So I'm going to bump our Excel and TI calculator computations into the beginning of tomorrow's video. So The empirical rule is the name of the rule that gives us a soft estimate for estimating probabilities that are associated with the normal distribution. And it is also, by the way, often referred to as a rule. I mean, that's like the stupidest named rule of all time right there, but it is really practical because it helps you remember exactly what you need to know. The 68, 95, 99.7 rule. I hate even saying it, but it's a pretty good practical name for us right there. What this is saying to us is this. In any normal distribution, I don't care what your mu or sigma are, if you are a normally distributed variable, then it will be the case that about 86% of all of our values are within one standard deviation of the mean. About 95% are within two standard deviations of the mean. And about 99.7% are within three standard deviations of the mean. I guess I was getting overexcited there earlier. I think I said 99.98% for something. That must be four standard deviations. We'll measure that like next class, literally, just to confirm that we can see it. So here's our graph of the empirical rule, or the 68, 95, 99.7 rule for the normal distribution. Notice that this curve right here is a standard normal curve, not just any old normal distribution, but it has an average of 0, and each standard deviation is literally 1 unit. So this is a standard normal distribution, but it doesn't need to be. Any normal distribution will follow this rule right here. 68% of the area underneath this curve is between one standard deviation below and one standard deviation above. 95% is the middle two standard deviations, and the middle 99.7% of all observations are within three standard deviations above and below right there. So drawing these intervals right here, like you're seeing up top, is going to be super useful for us. I want to do one other thing real quick here, is that the other thing I want to do is I think you should always be including another line when you're drawing, and by the way, you're going to draw a diagram like this a whole bunch of times here. I think drawing a middle line is also important here. It helps remind us that this is a symmetric distribution. As I've said already like 3 times this video, when we collect data, we always expect for there to be a little bit of variation in our data, a little bit of noise, a little bit of things being off from our ideal perfect scenario. But obviously this is a pretty nice idealized curve right here. And in our true normal distributions, we expect the left side to be an identical mirror of the right-hand side. So some other things that I think I can say, actually I think I just set up some questions about this graph right here. Let's just do these in this graph down here. Anyway, you should be referencing a diagram like this a lot this week, and then in the future we're not going to use this general rule as much, but this is a really good way to start thinking about our normal distribution. We will get more technical computations later. We'll see the limitations to this in a minute here. But this is really practical, and it's a really good way for you to not have to do any technology computations at all, except for maybe like a little addition, subtraction in your calculator, but nothing major. So let's see how we can use this rule to answer some interesting questions. So first question that I want to ask here is this. What is the probability that we see an outcome that is, let me do my typical thing here, give myself a little bit more room. I'm always, just bump that all the way down there. I just want to be able to draw some stuff on this curve right here. So here's what I'm seeing. My first question is, what is the probability that we take a random observation from a population and the observation that we see is more than 3 standard deviations above normal, right? So again, remember that Shaq is like 6 standard deviations above normal, right? So when we're talking just 3 standard deviations above normal, that's still like Michael Jordan and Kobe Bryant are both ballpark. I think they're like 3.5 standard deviations above normal. So they're obviously very tall people, but they're not like you've probably seen like one person in your life taller than Michael Jordan, probably, like at least. And so looking at our 68, 95, 99.7 rule right here, what I can see is this. If 99.7% fall here, then it must be the case that the remaining 0.3% is everything else that's out here, right? Because I know that to the left and right forever is 100% of all of our stuff. So what I'm observing here is that there's 0.3% that hasn't been represented yet, and that is going to be symmetrically spread out to our left and our right sides. So this should be 0.3% over 2, right? I'm splitting it up. And 0.3% over 2. And so it looks like we should really be experiencing 0.15% of all observations are more than 3 standard deviations above normal, and 0.15% of all observations are more than 3 standard deviations below normal. So 0.15% seems to be the probability of experiencing an observation that is more than 3 standard deviations above the mean. And the way that I got that was by using the 99.7% for the middle 3 standard deviations. That helped me figure out what should be going on with the outer parts out there. It's out of 100, right? Out of 100%, 99.7% were in the middle. The remaining 0.3% must have been split amongst the tails. And since there's 2 tails, I split that 0.3% equally among the 2 tails to get 0.15%. Right? Hey, just a physicist, how's it going? So maneuvers like this is what we're looking for here. So let's answer some other questions that are just like this guy here. What is the probability that we see an outcome that is less than average? And so let's notice here, I'm going to do my my dumb one right here, is just to say, if you go forever left and forever right, that's 100%. And so it should be the case that if we're looking at the probability that we see an outcome that is less than average, that we are looking to split this guy at exactly the halfway point of this thing right here. So this should just be 50%. And now, hopefully, this is not a surprising answer to you whatsoever. If a variable is symmetrically distributed, as the normal distribution is, then it should always be that half of our observations are above average and half of our observations are below average. Notice that this is different if we're in a non-symmetric distribution. Remember that when we looked at home prices, that these are not symmetrically distributed. It's more like this right here. The average out here is going to be like here because there's those couple like $10 million homes, right? Here, half of observations are not above average and half are below average. We don't get that in non-symmetric distributions out there. But because the normal distribution is symmetric, well, then we can say 50% are going to be below average, 50% are above average. So let's look at 2 more of these here. What is the probability that we see an outcome that is between 1 and 2 standard deviations below average? So it looks like what we are interested in here is this region right here. This is our region of interest right here. We want this. That's the area of interest. That is between 1 and 2 standard deviations below average. We can visual. Oh man, I should make that bigger right here. We're going to want to see more for this guy. So between 1 and 2 standard deviations below, this is what I want. So how am I going to get that piece of information of interest right there? Well, I'm going to need to do some funkier steps right here with this one, right? So I'm going to mark this as my. In fact, what I'll do here is this, so that we can clearly see this is the piece of interest. That'll get my question mark in red right there. That's the interval where I want to know how much of my area is contained there. So here's kind of the thing that I'm seeing. 2 standard deviations covers all 95%. 1 standard deviation covers the middle 68%. So I want to kind of maybe break this guy down into some finer chunks right here. So here's some things we should do. There's a lot of, by the way, there's like 6 different ways that I could think of to like come at computing this number right here using this rule. I'm going to just show one of them that I think is going to be more broadly helpful for thinking about others in the future. One thing I can do right away is say to myself, well, listen, if the middle 68% covers from 1 standard deviation below to 1 standard deviation above, and I'm in a symmetric distribution, then I know that half of the 68% is in the 1 standard deviation above interval, and half of 68% is in the 1 standard deviation below interval. So it looks like to me this should be 34%, and this should be a 34% in those chunks there. Right? Does that make sense? The other thing that I can see is that 95 minus 68, that's going to be what? How much is in the gap right there? Is that 27%? So what this says to me is that 27% should be split up in this chunk that's right here. So I'm thinking to myself, this chunk right here should be our 27 divided by 2, and this chunk right here should also be our 27 divided by 2. And again, the way that I'm getting this is I know that 95% of our data is within 2 standard deviations. If I chopped out to the middle 68%, the 1 standard deviation stuff, that should leave us with 25 or 27% remaining in the gaps between 1 and 2 standard deviations above and below. And since we're symmetric, I'm going to divide that 27 by 2 to find out how much is in the above gap and in the below gap. So it looks like this should be 13.5%, and this should also be 13.5%. So it looks like the answer to our question here is 13.5% of all observations in any normally distributed data should be between 1 and 2 standard deviations, either above or below normal, and just one or the other. If you want to be between 1 standard deviation and 2 standard deviations away from average in either direction, then we'd get 27%, right? But in this case, I was just saying between 1 and 2 standard deviations below average. So I just looked to use my 68, 95, 99.7 rule to estimate just the area of this little piece of column right here. And doing some subtraction and some division, I determined that value to be our 13.5% right there. So let's look at what now I'm going to call our last one for the day, since I'm not going to go into our technology use today, because it's just a little too late to start that. I'll do our tech stuff tomorrow. Here come our computations right here that we'll do tomorrow. So what is the probability that we will see an outcome that is at least 1.5 standard deviations above average? So let me go ahead and come over to my diagram here. And by the way, the really important thing that you should be seeing that I'm doing here is I am dependent on a diagram to answer every one of these questions. For this chapter, you should pretty much be okay, let me make this basically like a rule right here, and it's not like I can enforce this rule. You can do whatever you want, but if you're just computing a number of standard deviations away from average, like this guy right here, using these formulas basically that we came up with, using these two formulas, I guess I could agree that I don't necessarily need to see a picture for that. Basically, every single normal distribution probability computation you ever do should be accompanied by a picture with 7 values labeled on the x-axis. Here we have 9 values labeled. They went out to 4 standard deviations. You should draw this picture for everyone so that you can help visualize what you are interested in. What is the probability that we see an outcome that is at least 1.5 standard deviations above average? Well, 1.5 standard deviations above average is going to be right here. That's my z equals 1.5. Really, the question that we're asking then is, how much area is underneath this curve out here, right? This area is our answer. Right? What is the probability that we see an outcome that is at least 1.5 standard deviations above average? Well, here's our bummer. Our bummer here is that our 68, 95, 99.7 rule only talks to us about whole numbers of standard deviations. It only tells us what we can do with estimates that are associated with whole number counts of standard deviations. So we can even get pretty wild. If we come up to think about this guy right here, I could ask you things like, what's the probability that we see something between 3 standard deviations below and 1 standard deviation above? That's a perfectly reasonable question for me to ask that you can figure out with just the 68, 95, 99.7 rule, because 3 standard deviations below and 1 standard deviation above are both whole number standard deviation counts. As soon as we get into any observation where it is not a whole number count of standard deviations, we cannot use the empirical rule, the 68, 95, 99.7 rule, to make any reasonable estimates. What you can kind of see is that it's not like we could just chop one of these numbers in half, because this area is changing in a weird way, right? It's like a curvy top right there. It's difficult for me to interpret the estimate for that area. So basically what we're going to come down here to say is, all computations where we're doing some non-whole number of standard deviation stuff, we're going to really actually need to actually compute that thing. And so this is where we're going to come and look at our Excel and our TI calculator computations here. And this is what we're going to pick up with at the beginning of next video. So let me just make my concluding statement here. Cannot use empirical rule. 68, 95, 99.7 to estimate probabilities when z-score is not a whole number. So to answer this question, we don't have an estimated way to do this. We need to go to technology to help ourselves out with this. So the empirical rule is really nice because it doesn't require any technology. Honestly, like I'm assuming that coming up with these percentages in here probably seemed like a at first when you see these right here, but this really isn't that crazy. This is a really useful thing for just making like generic estimates and thinking to yourself like, oh yeah, like about blah 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 percent of people should be like that. We're not trying to get technical with the empirical rule here, but it's very good for making sort of estimates without really having to do too much math of probabilities of seeing events of a certain type out there. So you will see this in the quiz that's in Canvas right now. You will see this in the My Open Math homework for sure. And so empirical rule, pretty nice and easy. Maybe my last statement for the day is this. I would highly encourage you to go to Google and to Google empirical rule and maybe like the word normal or something like that, and then click on images and just look at a ton of images that will show up that are going to look exactly like this bell curve, but are going to have a bunch of these other like sub percentages all filled in for you. And that might be very helpful for you in making a bunch of the estimates that you're going to need to make on this week's homework. So I'd strongly encourage you to Google around for some diagrams that are going to be helpful for you associated with the empirical rule. And I recommend that you do that also in the quiz. I'll poke you to do that right there as well. So just for time considerations here, I'm going to wrap it up here for today, and I'm going to pick up tomorrow. We are going to start with using technology to get more exact computations of probability. We've got kind of a couple different cases that we want to consider here. I will do them in Excel, but I also at least have written out what the TI calculator computations are. And honestly, if you're using the TI calculator, I hope that you found that there are a ton of internet resources that will help you with doing these computations in the TI calculator here. So again, we'll pick up with these computations here tomorrow and then talk about sections 7.1 and 7.3. I'm also going to show you, I'm going to write a little bit of code so that I can show you some examples that are just not really manageable by hand. I'm going to roll about 20,000 dice with a program tomorrow so that we can see some really interesting topics for chapter 7 out there as well. So I'll wrap it up here for the day, and I will see you guys with some technology items for tomorrow and some of our more interesting concepts that are going to really make us understand why the normal distribution is so useful to us for the rest of the semester here. So happy Monday, everybody. I will see you for chapter 7 stuff and our technology use stuff in tomorrow's video. Have a good one.